Today I'm going to walk you through a little bit of building as a system, but I'm going to do it a little differently. I'm actually going to put the hat on. I'll show you my background a little bit. And we're going to step outside of all the really cool stuff that you do, the really good stuff, the fine stuff you do. And I'm going to give you a little bit of an idea what's sort of happening in this weird world of production building and building codes, and some of the strange stuff we're learning, and some of it you're just going to laugh and go, yeah, we figured that out a long time ago. It's good that people like Matt and me are finally getting it after 40 years. Okay, so building as a system. We're going to talk about the building science and why building science applies no matter what side of the voting spectrum you're on, the right or the left, because the science doesn't change, which is sort of cool. I grew up in the fine state of Michigan, northern Michigan. I had a mother and father that were involved in graphic design and architecture, and I grew up visiting family and relatives in homes that had earth for insulation and mass and glass. You ever remember mass and glass houses? And it was sort of cool, and I didn't know I would end up with a career that would sort of reflect it a little bit, but I do have a couple things I learned as a young child. I do have memories of some of those homes. And if someone were to ask me, how did you feel? I would give you two terms. I remember them being cold and smelling sort of funny. Now, it didn't mean that the concept was wrong. It just meant that there was some building science going on, because we do the same things out of other homes that are built to code. So we're going to talk about building science. I want to give you a picture of what's happening on the regulatory front. So myself, I sit on, I'm the chair of the Canadian Home Builders Technical Research Committee for the National. We're involved with CMHC, CWC, National Research Council, so on and so forth. I'm also on a 20-member committee that is the new Standing Committee for Energy Efficiency in Building, and we're the group that has been asked within 5 years to figure out what the code's going to look like by 2030. How many of you know what the building code is supposed to do in Canada by 2030? What's it supposed to do?
Zero carbon.
We thought that's what it was. She said zero carbon, but I'm just going to be really honest with you today. Carbon isn't part of the picture. It should be, but it's not. So I'm just going to be really straightforward with you on what's been given to that committee. The good news is there's a lot of good folks like yourselves on the committee, but I'm going to tell you sort of what the plan is. There's some good news, there's some bad news, but I'm just going to try to encourage you to keep doing what you're doing because you're having a big effect on other people. So, houses a system. Real simply, we know what that is, right? We know, we learned back in the, okay, I'm going to date myself, I'm a kid, I'm in the back of a 1975 Vega. How many of you remember what the 75 Vega was, right? I went all the way to California almost laying in the back seat with mom and dad. It was really cool. It was the only other car John DeLorean designed before he went to jail for his cocaine habit. During that time, sort of a little bit before the end of the time, I also have a memory as a child in the city of Lansing, Michigan, of being in a gas line. Okay, we're down on Michigan Avenue near the state capitol, and there's a line of about 30 to 40 cars. Dad's in the vehicle, and we are allowed to have 5 gallons of gas. What is happening?
Oil embargo.
Oil embargo. Happened in the US, happened in Canada. We all of a sudden were in this crisis. And one of the first things we did was we discovered we needed to use less energy. And very quickly, Canadians and Americans and many others decided that one of the ways to do is to reduce how we use it, to reduce it in homes, to reduce it in vehicles, to reduce it in lifestyle, and it really was a moment of awakening. But what the interesting thing is about a moment of awakening is we often do things that are really dumb, but that's okay because they're lessons for the future, right? So you have heard the story. I'm going to pick on the Canadians now. I'm a Canadian citizen as well. US did the same thing, just so you know, they just did different acronyms. One of the first programs that the Canadians came out with in response to that, because we had the old Trudeau on the television telling people to put sweaters on and turn the thermostat down and sit next to your fire, right? The other thing too was that there was a program called the Canadian Housing Improvement Program, CHIP. How many of you remember this acronym? Okay. And under this program, you could go out and stick stuff in your attic that had never had insulation before. You could put stuff in walls that maybe had a little horsehair, and the government was going to pay for it. All in the name of energy efficiency. A little bit of vermiculite. Might have had some bad things in it, but we did it in the name of energy efficiency. And we were about to learn one of the first big lessons about house as a system. because we put it in attics that had never had insulation before. We put it in attics that had very little insulation, and what happened within the first year to two? We had moisture problems. We had attic rain for the first time. We discovered attic rain, which is sort of interesting. And we discovered in the walls, we started to have issues that we had seen in the past. You know, when we started insulating homes even in the late 1600s, and let me just ask you this, why did we start insulating homes years ago, our forefathers and foremothers? Was it because of energy efficiency? No. Why did we start insulating homes? It was comfort. Good grief. Who cares how many cords of wood we burn? And let's remember that. The primary reason we want well-insulated homes is because we need to live in them. But anyways, I'm off topic. So let's go back. So we insulated these attics, we insulated these walls, we started to have issues with paint spalling, we started to have mortar coming off blocks, we started to have issues with shingles, and we discovered that if you were going to change the amount of thermal energy in the wall by slowing down the movement of energy from warm to cold, from wet to dry, that you have to stop the flow of moisture. We discovered that in 2 years. And out of that discovery, we learned if you're going to insulate, you have to stop the movement of what? In cold climates? Air. Air barriers. First house as a system lesson. So, the CHIP program became the ARP program. ARP, Attic Removal Program. That's not a play on acronyms, that's what it was called. Insulation came out, air sealing went in, insulation goes back in. We get into the early 80s. What was the next problem we had? We now have insulated, we now have airtight, now what happens to the homes? Some mold, we got some condensation, we have some humidity issues showing up. We have a few people that happen to have some combustion-based appliances in the basement that all of a sudden are getting sick. Like my grandma and grandpa's house in Michigan, I thought it was sort of normal. That black soot stain on the hot water tank was just normal. Everybody had it. It was a mark that it was working, right? It's called flame rollout. It's what happens when grandma turns on the range hood, turns on the bath fan, the wind blows the wrong direction, the house goes negative, and we get carbon monoxide back in the house. It's not a good thing. So the message is house is a system. If you're going to insulate, you have to make it airtight. If you're going to make it airtight, you have to ventilate for the people that breathe. You don't need ventilation if you don't have breathers in the house. And provide combustion air. And there's another one, makeup air. So that's what it is. The one thing we do have to understand, though, is that houses are changing. And I'm going to talk about the grand scheme here. We have houses, we have more multifamily houses, we have occupancy loads that are changing, we have more glass in house than ever, and I'm going to show you some of those figures today. Houses have gone from your first time single story, we now have people living in 3- and 4-story homes. You go in, you go upstairs from the garage to your kitchen, you go up another set of stairs to your living room, you go up another set of stairs up to your bedroom, and then you go upstairs to your den or your loft. Can you imagine what it feels like in the top of that building on a warm summer's day downtown Toronto? And guess what? The air conditioner ain't going to do it. You're not going to solve it. You're not going to keep them comfortable. This is about controlling heat gain, solar heat gain collection, and possibly even zoning your mechanical system just to keep people comfortable. So things are changing. Expectations. The one thing we always say is that, yeah, codes are moving, but the thing that's moving faster than codes is the expectations of the people we build homes for. And it's not just the people we build homes for, it's you and I. I grew up in northern Michigan. I knew that it was winter time because the t-shirts and shorts disappeared from the shelf and mom put the corduroy in the sweaters in. We have 4 children. Our teenagers now complain in our net zero home, which is really, wonderful and it's sort of cool, that it's a little cool in the basement, Dad. Well, it's minus 28 outside and you have a t-shirt and shorts on. They're our children. So, again, it's not a matter of if with some of these changes are coming, it's a matter of when. And that is good news for folks like you that have been doing a lot of these things for a long time. Mainstream is finally learning some of the things that you have known for years. But it still doesn't take away from the fact that it's a good idea to step outside and look across the spectrum of house building around the world, south of the border and around us, even to code builders, to find out what they're doing and what's going on, because you need to learn from their mistakes as well too. The science is the principle. Now, really quick, You know that 2 years ago, we had another change to the building code. So for houses, we had a 15% jump in energy efficiency, and for buildings, part 3, part 10, we had about a 10 to a 13% jump, up we go. And for the first time, we had to address a little bit like thermal bridging. We had to actually have those weird machines in houses, you know, the boxes that everybody unplugs that bring in fresh air, HRVs. We had to put in drain water heat recovery, whatever that is. And this is what the proposed changes to the building code looked like. This came out 2 years ago. The proposed changes were that by next year, mandatory blower door testing, minimum R5 on the outside of all walls. Why? Because you're controlling your dew point. And Canadians knew 50 years ago. John Timmis, my old professor at U of T, has been teaching it for 40, 50 years. Control your first condensing point. Get the insulation on the outside, and we're now just starting to talk about it being in the code. Anyways, that was all fine and dandy, and then we had an election. So, here's the good news. Yes, they've stopped those changes. We're not stepping back. We had a meeting, I sit on the OHBA technical committee, and it's very interesting to be there with some of their members, the Ministry of Municipal Affairs and Housing and so on. And the reality is they have stopped with those changes. They're going to reconsider them. We might have to stay put for a couple years. But here's the thing, folks. Whether or not we stay put for a few years, it's going to continue to go up. And if they do decide to adopt the National Building Code of Canada, it's like getting off an elevator and onto an escalator. Because the NBC, by 2030, 2032, is headed towards net zero ready energy anyways. Not quite carbon, but it's a little step that direction. So this is from the Pan-Canadian Framework. Many of you have heard about this. This is the premise under which the National Research Council, the code committees are working right now. I want you to look at two things on this. One is homes and buildings. The other big fish to fry, though, is the one at the bottom. It's 99% of our building stock. It's the stuff that's already built. I can tell you on that committee, we can sort of figure out maybe what it means for new homes and buildings, but when it comes to existing, that's no man's land. That's what we're going to be spending most of our time on, and we're going to need all the help we can from people like you. And I'm not just saying that to make you feel good. This is the approximate steps we're looking at by 2030, 2032. Ontario is already at sort of the second tier under its current building code. BC's got their step code already in place. You've seen this. BC has the step code. It's a bit of a microcosm of what national is going to look like over the next few years. You know, that tier 5 being net zero ready or passive house or whatever it may be. They're moving towards it. South of the border, I just want to talk for a minute. You know we had an election down there 2 years ago, right? Okay. So we have a company in the US. We work with, of the top 10 production builders, we work with 4 of them. Some of our clients down there, Lennar, who bought Cal Atlantic, will build 35,000 homes this year. So we work with the big bad production guys. Here's the interesting thing. We work in about 35 states. This is the code in the US for houses. They call it the International Energy Conservation Code. International because they're very ethnocentric. 2006 was the first time they had an energy code in the US. First time they had anything in a HERS rating, home energy rating score of 110. So you're at, what is it, a 2x4 wall with R10 in it, with R30 in the attic, single pane windows and nothing under the ground. That's what that is, let's call it. Then they adopted the 2009. It's 3-year cycles. Now, it's up to every state to adopt whichever one they want. The thing you need to understand here, though, this is actually an interesting one, is that we are now at the 2015, and now there's a 2018. And here's the cool thing. In the last 2 years, there have been 4 red states. Do you know what a red state is? You guys watch TV? Okay. 4 red states that have adopted the 2015. My home state of Michigan, Republican state, a year and a half ago, adopted the most stringent energy efficient building code in the history of the US. Why did they do it? They got confused, right? They hit the wrong button at the voting booth. Here's why they did it. Same reason Minnesota did, and the same reason why Texas is between the 2012 and the 2015. Texas has the largest net zero community in the US, just so you know that. Here's why. It might not be carbon they're concerned about, but the one thing they are concerned about is crappy houses and houses that use too much energy. The good news for us, the good news for you here is it means they're at least headed in the right direction. It is now illegal to build, close, and occupy a home in the state of Michigan without a blower door test. Wow. At 3 air change? Okay, we give them credit. And to have duct leakage testing done to make sure that it's no more than 10 to 15% leakage. We don't even do that here. How many of you, when was the last time you actually tested system performance on your mechanicals? I know, same here. So again, cool things are happening. But again, and I'm not saying this to make you feel good, it's because people like you have been doing this for a long time and they're finally starting to figure it out. What's a net zero home look like? I've used this slide at the national level to try to get people an idea what it means. We get asked often. We did 98 net zero homes last year with some of our production builders trying it out. We've got several net zero sites. Sifton has a W5 site in the city of London, Ontario. Their first 110 units are in. What does net zero energy look like? It looks like this. You look at it and go, well, that's probably the houses you build every day. These are effective R values, by the way. R60 is pretty well code. R22 2x6 wall with R10 on the outside. Basement, pretty well the same thing. Under slab, R10. Remember, this is just what we say just to get in the game, right? This is just a net zero ready, just to get the load down. Windows R6, what's an R6 window? We try to keep these in layman's terms. This is a window that's got a U value of about 1.1, 1.2. It's a triple. You can call it what it is until they come out with vacuum seal glass. Robust air barrier, 1.5 at least, or better. And mechanical systems, it's right size dual fuel or all air source heat pump or geo, and an HRV or ERV with ECM, and condensing hot water tank or an air source hot water tank. That's it. One of our larger clients, Mattamy Homes, Great Gulf, Reed's Heritage, Doug Terry Homes have now done the pricing for them to get to net zero, ready. Without solar, anybody want to take a guess on how much they think it's going to cost them? Nothing? Almost. Used to be $150,000. Remember the Equilibrium program, CMHC? We added $150,000, $175,000 to make those homes net zero. They were a bit more efficient than this, but this was the general target. Then we did a bunch of communities across Canada, net zero pilot with Owens Corning, NRC. These folks are down to getting to net zero ready for about $6,000 to $8,000. So it's a double-edged sword, right? We're going to say, why don't you just do it? Some of them are starting to get that, but the good news is we're getting closer. All right, here's the loads on houses, though. Here's the thing you got to understand. This is a typical two-story home built to building codes back 30 years ago. This was sort of the consumption. 200 gigajoules was the total energy consumption. It was about 19 to 22 tons of greenhouse gas. Now, this is based not just on site, but also source in the Toronto area at the time. There was no AC. The biggest load was heating, right? Don't have to be a statistician to read that graph. Now you come to the 936 current building code or the Ontario Building Code Package J, or I'm going to say A1, the pie has shrunk by 60%. What's still the biggest load? Heating. What's the new load? Wasn't there years ago? Cooling. What's going to cost you more, heating or cooling? It's weird, right? You want to save energy, you do the red. You want to save money, you do the blue. It's sort of odd. Here's the thing, we're down to 10 to 11 tons for most cases, annual consumption 115 gigajoules. Remember, to get down to a house that will only need 9 to 10 kilowatts of PV, 700 square feet, 750 square feet, you've got to be down to about 35 to 45 gigajoules, GJ, somewhere in there. So there's that house. Here's your net zero home. What's the biggest load? So now you know your biggest fish to fry. It's you. I'm not going to show you the slide, but we built our net zero home. We've been in it for 4 years now, and we were net zero until the day I got a phone call from Rachel, my wife, that said it is 98 by 96. And I said, what do you mean? And she says, listen, she said, this is 6 houses in 12 years. You know this is the last one, and you promised me 3 houses ago that we would get a hot tub. Our biggest load in our home, we've been monitoring every plug load with the NRC and with CanMet and Mitsubishi. Our biggest load in the house is heating and cooling. What's our second biggest load? Yeah. So, consumers. Here's the thing about the consumers, and I want you to remember this. Sales and marketing. This is your competition. Don't ever forget it. This is sort of cool. The stuff that you build now solves all these problems. So don't just market it because it's going to save money. Don't just, and you guys know this, you're talking about healthy housing here today. You are solving the crisis for all of North America. The boomers, they've done many studies on the boomers, very large age group that we have with us. Some of us almost there, borderline, right? Some already there. The two main concerns of the boomers in North America are predicated on two things. The very top concern is what with that generation? Health and wellness. And you just solved it. The next one's pets. See what you can do. I kid you not. All right, here's the other good news. This is a survey done by Avid Surveys. Avid is a builder rating service company that we've done work with for years. They rank the largest builders in Canada down to the smallest. They're the largest of its kind. They actually took over for J.D. Powers, and they do the largest consumer engagement study in North America. This is larger than anything done by the NHBA. They give homeowners a list of 128 to 136 items. Homeowners that have either bought a home in the last 6 months or are going to buy a home in the next 6 months. 3,000 to 4,000 of them. And they ask them, it's a long survey, which is really interesting. They ask them, which of the items on this list do you feel have to be part of your home? Not, what would you pick if you had an extra 20 grand? This is an interesting list. We have builders and we have salespeople that look at this and go, huh, really? Sure. Yeah, the last time I sat in a sales office, someone walked in and says, do you have ERVs in your house? It ain't happening. Here's the thing we have to remember. People do not walk into sales office asking for these things, folks. They either assume you got it, and if you don't tell them, they don't know what they're missing out on. And it's one of the things that we as an industry take for granted. What did Henry Ford say? If he had asked the general North American what they wanted, they would have told him they wanted what?
Faster horse.
Faster horse. They don't know what they want. It's up to us to help them understand what they need. Anyways, sort of an interesting one. 3 themes in the top 10 list across Canada this last year. We need storage. We all get that, right? Especially the condos in Toronto. Kitchen. We like our kitchens. It's a living space. 3rd on the list. Health, comfort, efficiency, third-party labels. Good grief. Anyways, sort of cool. So third-party validation, 22% of all starts in 2017 had something like this on it. The new Energize system, you're familiar with it, the program that underpins Canadian housing, not a bad system to use, but that's the new guide. There is a move afoot at the national level to start to identify the requirement for this on existing homes. I would probably put a thumb in the air and go, we've got about 5 to 8 years and we probably will see it. We were this close to getting it in Ontario, and then we had an election. I don't know what you guys did for voting, but anyways, you ruined it all. So they, I'm joking, the Home Energy Rating Disclosure Act, we're about this close to it, and we're starting to even see it happen state by state in the U.S. To that point, lots of benchmarks around the globe, this net zero energy type of thing. No, it's not net zero carbon yet. Let's be really clear. It's a step towards that. You have countries where they're already there, and the reason they're there, quite frankly, is because it's 50 to 60 cents a kilowatt hour to get their electricity. So it's been bad enough for long enough. That's a nice little real estate on the right. That's a sales, mandatory labeling in France, as it is in Germany. You buy a home in Germany or you go to sell your home in Germany, if it does not meet a minimum efficiency level, you're required to upgrade it. If you choose not to, you post a bond against the home so the future purchaser can actually upgrade the home. The consumer. So here's the thing though. Energy efficiency is great. Low, no carbon is great. Question is, how's the house feel? And that's what we've got to be careful of. And I love your topic this year, healthy house, comfortable house. Robert Bean, if you ever want to have a guest person, maybe you had him here, get Robert Bean out here. He's former chair of ASHRAE 55. Recently I was on an ASHRAE committee with Robert Bean. It's the new 90.2 for the low rise. 90.2 ASHRAE has now adopted ASHRAE 55 as basic fundamental principles. In other words, you have to meet the tenets of ASHRAE 55, which is sort of cool. If you design a home for human comfort and health, you magically end up with the same home as if you designed it as a low-load, net zero ready home. It's sort of cool. Anyways, I think Chris Magwood can help you better out than I can and Melinda on that one. But anyways, so here's the thing. Thermal comfort is, the reality is there is nothing in our building codes about thermal comfort at all. If we changed one sentence in the building code, according to Robert Beam, that we were to maintain human comfort based on ASHRAE 55, you would immediately be at a minimum building code that was the net zero I just showed you. Warming the surface temperatures, warming the walls, getting rid of your condensing dew points. Sort of cool. So, Rocky Mountain Institute, we measure comfort based on a thermostat. You realize the thermostat was invented to simply make sure your appliance was working. It was not invented to make sure you were comfortable. The worst thing we ever did with thermostats was put numbers on them. If you're uncomfortable, just turn it this way. Right? Anyways. Yeah, it's incredibly important to building occupants. The traditional air temperature-centric design is outdated, it is not useful, and it's invalid is basically what they're saying. So when you design a home, let's start to think about ASHRAE 55. It's not hard to use. The good news is it doesn't have to be the P-Engineers anymore and the really techie people to do this for you. You can go on websites now and do this on your own. University of Berkeley, California, UBC has a calculator you can use. ASHRAE's got a nice little calc you can use. Shoot, I'm going to show you in a minute. You can go on Cardinal Glass's website now on the Human Thermal Comfort Calculator and put a person in a room and figure out if you're going to be comfortable. So the tenets of thermal comfort are multiple things. I just want to show that to you. Aside from the personal factors, which I'm not going to get into today, the three main things are your air temperature, your ambient, your surrounding surface temperature, which is the temperature of all the surfaces around you, and geometry does have to do a lot with that, and humidity. These are the things that make you comfortable. The thing that we need to remind ourselves is the Canadians have known for a number of years that the largest component, 50%, is your radiant heat exchange with the surfaces around you. This is why nobody likes to sit next to windows. This is why we have Aunt Em's duvet that she made 50 years ago on the back of our couches, right? Because the couch is next to a window, and the window is cold. And even though the thermostat tells you it's 26, it's lying to you because you are losing your body heat not to the 26-degree air, but to what? The window that's at zero. You realize that a meter away, all it takes is for the surface temperature to hit 14 degrees C, and your antenna in the back of your brain goes up, and you start to feel chilled. All right, consumers, let's remember some of the lessons we've learned, and we're still learning them. How many of you are involved in the Equilibrium program houses? There's some cool stuff. Very successful homes. You want to like watch some cool videos. The videos they've done of the homeowners that have lived in these homes are phenomenal. Put them in front of some of your clients and let them listen to it. Anyways, some things. These are some of the things that we've taken into account when we try to build the things. So they actually interviewed these homeowners that lived in these. I think at the end of the day there was only nine or 10. I think originally there was 15. Homes across Canada, every climate zone. They spent anywhere from $125,000 to $250,000 making these homes net zero ready with lots of green things, lots of healthy features to them. And the idea was CMHC was going to come out with a net zero home program. And the reason they called it Equilibrium is because they thought no one knew what net zero meant, but then they found out no one knew what equilibrium meant either. But anyways, that's okay. We learned some cool stuff. So here's the thing that they learned, and remember, take these things to heart. When they interviewed the people in the homes, the first things that came to mind that they really liked was, it was comfortable. Some of these folks said, we bought the house, figured we're going to flip it in a couple of years. The problem is we are now concerned that we will never find a house that feels, sounds, or smells like this house again. Cool, ruin their appetite for the status quo. The availability of ample natural light, really nice. We've gone from 4 to 6% window to wall ratio in the late 1980s. We now have houses coming across from production builders at 22 to 25% glass. Why? Not because glass is cheaper than the wall. People want light. Superior insulation, soundproofing. Who knew? We were building homes, so I was head of operations of a company called Reed's Heritage Homes for 12 years. We did Canada's first LEED certified home in 2007, and we did some net zero stuff. Our buttons are popping off because we're so proud, but we learned a lot of interesting lessons too. And one of the things we learned is, hey, did you know that if you make a house airtight, you pour more insulation on it? It gets quiet. And people like it. That's sort of cool, isn't it? Anyways. We thought we discovered something new, but you guys knew that. Ability to control, and this is an important one. They like the ability control, but it was a double-edged sword because the negative on some of these homes was the inability to control. We're working on a Living Building Challenge home in North Vancouver right now. In the charrette, the homeowner was there with her 3 interior designers and her interpreter. They have 2 estates that are highly energy efficient in Asia, and her main concern with building this home wasn't the energy. She said, I do not want to have to control this house. Our homes now are too complicated for our family and my aging parents who live with us. So give us a home that runs itself. Whoa. Oh, and by the way, 35% glazing. They want to have perfect temperatures at every level of the house. We brought Robert Bean in on that one. Anyways, high quality, comfortable level of humidity, better indoor air quality, low maintenance construction. These were things that they loved about their homes. Concerns, and again, we learned from the past. Some of these technologies, there was issues with performance, complexity, noise levels. One of the things that was a real, I'm going to say downer, was some of the solar thermal systems. Solar thermal is great technology, poster child technology for years. The problem is a lot of systems are engineered, and it's okay if your Uncle Bob, who's from the Canadian Space Program, lives next door, but for the general consumer, when something goes wrong, it's really tough to fix those systems. So someone's going to get it right. Many of you have probably already got solar thermal systems right. What we see is there's a huge vacuum in that market for someone to come in with a good turnkey systems. Unattractive landscaping, personal taste, difficulty cooling the home. Almost all these homes are based on the premise of natural cooling. We don't need AC. Okay. Be careful. Here's the problem. Many homes that don't need air conditioning are okay sometimes with people that understand that they need to do certain things. Close shades, open windows, close windows. Sometimes. The problem is that's the Smiths that you built the house for. The Jones are going to buy it and move in. Now they don't want to have to do those things. They don't understand. All they know is they want to be comfortable. And we now have energy efficient glass in buildings that are allowing so much heat into the house because of mass and glass that you now have a 4-ton cooling load. How do you change that? Okay. We also have another cooling element that's going up because of climate change, and it is not temperature, it's humidity. We are seeing high levels of moisture, higher than we're used to. So again, some things to keep in mind. Overly complex automation, so on and so forth. Won't spend too much time on the negative. I love this one. Comfort delivers sustainable homes far exceeded homeowner occupant expectations. The amount of natural daylighting, sound insulation, ventilation, all those things, ability to control temperature. The cost of purchasing the building, sustainable home is not prohibitive because they were able to offset it with some of their energy savings. None of these homes, by the way, actually hit net zero, just so you know that. None of them had a zero energy bill, not a single one, but there was not a single complaint. All right. Building science tipping point. How many of you have ever heard that term? Sort of interesting, isn't it? We have Sam Rashkin, Chief Architect, Department of Energy in the U.S., invented the Energy Star for Homes program, Zero Energy Home program. He loves Canadians because he knows that that's where all the good building science comes from. So he comes up here once in a while, gets refreshed from folks like you, and goes back home and tries to convince them. He coined this term because he knew that as the codes increase, this is what happens. More insulation, tighter envelopes, we are at risk of comfort, we're at risk of water details, and indoor air quality risk. And he imagined and analyzed that this would happen at about the 2009-2012 IECC change in the US. And they've seen it. And this is what the point he's trying to make is it's fine and good to add lots of insulation, it's fine and good to make things tight, it's fine and good to do lots of passive things, but you have to remember house as a system. Things get more complicated. The houses react differently. They actually react faster, and at the same time, you have people that have higher expectations than you've ever realized. So we have to be careful of this. I will give you one example. The picture on the left. There are 2 class action lawsuits in this province right now on homes that have no flashing. And it's not just homes, it's homes plural. Here's the thing. I know you all do this, so that's good. If you do not flash windows and doors now, do not build another home or building until you figure out how to do it. Because in homes that had little bits of insulation, that had air leakage, when the walls got wet from rain, they might dry out. You had a big hair dryer in the house called the furnace, right? Energy's moving through the wall, energy's available, it dries the house out. As soon as you make it tight, as soon as you start to change the temperature differential, and I don't care if it's a double stud, breathable wall, right? It can vapor flow, can go both ways. Guess what, folks? When you do double stud walls, it doesn't matter whether the wall could dry in or out. You have fundamentally changed the temperature of the outboard surface. And if you have water coming from a window or door leak, there is no wall that can dry fast enough to save your soul. Okay? So here's the thing. If you are going to add insulation, make homes airtight, get your windows taken care of. Now we often get the question, is it in the building code? It is. Get familiar with this thing called the CSA A440. The Ontario Building Code, the National Building Code references the CSA A440, and it tells you, I'll give you an example here, 1021, you shall have subsill flashing that includes a 2 to 4% slope, plus back dam, plus end dams, done on which doors in Canada? How many of you do renovations? Which opening on the house is the first one to blow apart because of water? Patio doors and sliding doors. They're the doors that see the most water infiltration. There's no roof over top, so you have no deflection. First rule of water management. The other thing too is you put a deck at the bottom, you now have splashback, so you have 40% increase in water deposition on the bottom of that door. 22% of all windows and doors for the last 4 years in Canada done through the Siding Windows and Doors Association contractors have been done on homes less than 10 years old. And almost all the reason for replacing it was because of no flashing. So I will get off my soapbox. So the question is, we know net zero is not an experiment. We're going to get there. The code development's changing. What at minimum should we be looking at? And some of you folks are already doing this stuff, so just bear with me. This is what we're trying to encourage builders, designers, and everybody else to put on their agenda. If you're going to stay relevant, these are things you need to consider. We've tried to put it in order of importance just to keep things safe, keep things right. Air tightness and water management should be at the top of your list. Right? It's the things that keeps buildings and makes them sustainable. You can put all the good products you want in a house, but if you don't manage the water, you don't manage the air, it's all for naught. Better windows than your wall and basement insulation, domestic hot water, get some fresh air, mechanicals, renewables, and storage are all on the gamut. Forgive me for some product pictures. I'm not endorsing anything, so close your eyes and pretend you don't see the color or the fact that it's foam versus anything else. So where do we start? When we look at a house, your largest heat loss, a typical home in Ontario today, if you were to break apart the heat loss portion, remember that little pie chart, this is what you would find for heat loss. So where do we start now? Biggest piece of the pie, air leakage and ventilation. Where do we go next? Basement. Are we going to the attic yet? Not yet. Where do we go next? Walls and windows. This is an interesting one. As a builder, it used to be, I'm going to put window insulation on the wall, I'm going to put a lot more of that early stuff and get it, and then the windows, yeah, I'm going to think about that when the prices go down. Oh, wait a minute. Windows now, and I'm going to show you a slide in just a minute, if you have enough windows in the house, it's actually more beneficial to do triples than it is to add insulation to your wall. Again, house is a system. So let's take air tightness real quick. Here's the thing you got to understand with house as a system with air tightness. Air barriers were not put in the building code because of energy efficiency. I'll say that again. Air barriers and air tightness were not put into the building codes of North America, Canada, or the US, or any other country for that matter, for the sake of energy efficiency. It was because we don't like this stuff. When people talk about houses that breathe, these are houses that breathe. Air leaks out, condenses on the first solid plane, and if it's wet enough for long enough, our good friend Dr. Straub and ornery old Steebrook would say, you get bad stuff happening. It's like a game of Risk. We see it as attic range as well. Now, here's the thing. In the early 1900s, again in the 1800s, when we had prevalence of lots of different insulation types going into homes because people were uncomfortable, we started to see things like paint start to blow off houses. We started to see paint on brick come apart, mortar come apart, and the reason that it was happening, we know now, was primarily air leakage. But at the time, believe it or not, the paint manufacturers actually sued the insulation people. And they brought a gentleman, I don't know his name, but he deduced through what they knew at that time in science, it was because of vapor flow, right? So we talked about vapor barriers, and that's why we started to see craft face bats. We started to see in old walls, you'll often see a layer of rag paper, tar paper on the end just behind the lath and plaster, because they thought that if you control vapor flow, not airflow, vapor flow, that the paint wouldn't peel. The reason is they had part of it, but they didn't understand the air leakage. That wasn't until really back around the 1970s, 1980s. So here's a typical picture. This is the amount of water that gets into a wall through vapor diffusion, right? Little bit, third of a liter of water, it's about a pound. It's about 2% of all water in walls is from vapor movement. Then we discovered in the 1970s that it was air leakage that was the predominant carrier. This is a very old slide from the R2000 program years ago. Been around a long time. The Americans like to use this. The building code, again, in Canada, in Ontario, has air barrier systems. There's 16 points where you have to seal it. They assume that homes are sealed at 3 air change to 3.5. If you do anything with any of your homes now, many of you already do it, but start to learn how your homes are performing. Because fundamentally, in the world of engineering and metrics, you can't improve something until you measure it. And then there's a magic that takes place when you do measure something. What does it do? It magically improves. Now, mad at me. It's not a good word, but I will say on their behalf, they blower door test every single home. Not many people know this. They all hit single detached 2.5 air change. It's a little step, it's a little something, but it is sort of something, right? So hopefully they're getting it. Current building code, 3 to 3.5. Proposal is to take it to 2. By the time we get to 2032, you're going to be at 1.5 or 1. Strive for 1. What's the best air tightness score anybody has in the room? This is always an interesting one. What do we got?
0.15, 3-story, 34-unit apartment.
0.15. Now, the question for you, were you able to take your infiltration numbers, put them into your mechanical calculations, and actually right size the equipment?
The mechanic system aside for 0.6.
Ah.
So they weren't that optimistic.
Interesting. I think it was John Coco or Richard Lay that have often said that's one of the things they've wrestled with for years, is trying to get on the mechanical side to take the infiltration numbers and to use them appropriately and then actually right size the equipment, because if you don't, you end up having to do lots of commissioning changes on the fly to get the mechanical systems to work, because the building's actually much more tight than you thought it was. Anyways. Okay, continuous exterior insulation. We know we're going to get there in the next few years. We know that our walls typically are made of wood. A typical house frame today, 16-inch on center, you've got about 22 to 23% of your wall is wood, and then you have what we call wood storage. Some wood, not real efficient framing. They're going to tell you there's a point load up there. It was the framer over in Minnesota, and the builder, the VP of construction, was telling us how efficient they frame, and they do value engineer. He's walking through the homes, and he sees all this wood in this wall. He says, "Oh, where'd that come from?" He goes get the framer. "Come over here and tell me, where's that?" He says, "Well," he says, "we do that in all our homes." He says, "What do you mean? That's what we said." "No." He says, "You always need a stud here or there." He says, "We just sort of stick them in the wall." He says, "What do you do when the house is done?" "We just leave them there." Okay. Interesting. Here's the other thing why continuous insulation on the outside is important. I'm not going to worry today. You folks know more about the concerns about what it's made with, and that's what I want to learn from you. But the one thing we do know as Canadians in particular is it's about controlling the dew point. This is your traditional wall. This is an R20, R22 bat, code-built wall across Canada, 2x6 wall. This is what happens at the back of the OSB or the plywood sheeting when it starts to get cold. What we have here is what's called a risk curve. Those of you in building science have done these for years. You've probably taught all your students about them. Here's the thing. Guess what we're starting to see when we do forensics for the Atlantic Home Warranty Program and for Terrian in the field now? Black staining and mushy stuff on the back of OSB and plywood. And this is why. It doesn't happen on every wall, it just happens on some walls. It's weird. Might be because it's pine brick and it's south facing. We don't know. Anyways, so what happens is there's a risk curve. So how do you get rid of this risk curve? How do you stop How do you warm up that surface? Well, the easy answer is let's just take the relative humidity in the house, right? That's what the building codes assume. 35% is what they assume in the wintertime, 21 degrees C on the inside. If we just take the air and take it down to 10%, we should get rid of most of the curve. And how are you feeling? Right? You can't do it. You got health problems then. So the reality is 35 is about the minimum that ASHRAE recommends in the winter. So you simply put R5 on the outside. Who knew? This has nothing to do with vapor permeance yet. We aren't even there yet. We're not even there talking about whether the wall has the ability to dry one side or another. We're just starting the basic conversation that you've got to control the dew point. This is why the National Research Council is positioned that in the next 3 to 4 years in the next National Building Code, they will be requiring at least R3 minimum to possibly R5 everywhere, period. They're not even going to worry about vapor permeance because this is really the biggest deal, controlling the dew point. How many of you have seen the studies from the Coquitlam hut, test hut, Vancouver? This is sort of cool stuff. So, a builder, actually a little bit like yourselves, out in Coquitlam, North Vancouver, heard all sorts of things. He was told by people you can't build those walls that have like low perm insulation materials in the outside, and walls got to breathe. And then he was told for code you got to build an R22 wall with interior vapor barrier. And he's like, so I'm hearing all sorts of stuff. Like, what actually lasts? So he called up Joe Steebrook and John Straub one day and says, listen, fellas, he says, I have an office building, I'm retiring in about 5 to 6 years. If I build a test hut on the top of my building, would you actually test walls? And of course, building science geeks like that are, sure, let's do this. So they built a test hut in Coquitlam. Now, if you look at the hydrothermal zones for North Vancouver, it is one of the areas in Canada that if a wall or a building enclosure is going to fail first, it fails there. You've heard of the leaky condo crisis, right? Okay. So they built multiple walls. They built walls that were code-built walls. They built walls with exterior low-perm foam, high-perm, all sorts of stuff. And they even had water deposition. Chris Schumacher tells about putting little drops of water in the walls to simulate leaky windows and doors. And now, I know I'm oversimplifying this, and many of you know this study better than I do, but I just want to bring back this point of controlling condensation. The wall on the left is the building code wall. The wood at the base of the wall, the plate, the bottom of the stud, and the sheathing was at 24% moisture content. Can you legally build a wall that has 24% moisture content? What is saturation for SPF? It's only 29. 29% is when all the voids in the fibers are filled. Not the cell themselves, but all the voids are now filled. 29% is. So we now have wood that's at danger of decay. We're almost to the point where if you stick a framing nail in, it might stick back at you. Depends on what your PSI is on the gun. This is the one of the walls that wasn't supposed to last. This had a low perm foam, type 3-4 type foam on the outside. And again, what it did is it validated this fact that if you control the first condensing point, that you build a better wall. Now, if you build a wall that's got leaky doors and windows, all bets are off. Let's just take that out of the picture, right? Just some things to remember. So this is why we're moving towards continuous insulation on the outside. Really, it's more about durability and everything else than it is about energy. Windows. A couple things we learned about windows. Lots of things to consider. Solar heat gain, air conditioning loads, comfort is a huge one, and condensation. These are all things that clients are concerned with. So things that we know is that architects like glass. We have a house 2 years ago, the best one we've seen was 65% glass. So, and they were worried about the R value of the wall. We told them, no sweat, don't worry about the wall, get good windows, you'll be fine. So, the amount of glass in houses, according to CMHC and the CHBA, has gone up from 8 to 10%. We now see most of the building stock at around 17 to 25%. We did a study for Fenestration Canada along with Jeld-Wen and 2 other window manufacturers a couple years ago, found out that actually if you're going to, and I'm going to say between 17 and 20% window to wall ratio on a house, which, does that sound fair? Sort of normal? 22, you got to do energy modeling and fancy stuff at 17 to 20%. That if you put a decent window, a tri-pane, a 1.1 U value in that house, you add more effective insulation value to the entire enclosure than putting R10 on all the framing. I would rather be in the window business at this point than in the insulation. Sort of interesting. Now, There's a lot of ifs, ands, and buts about this. This is a very generalized study, but what it's showing is something that you folks have known for years, and we're now at that tipping point, is that glass is really a big deal now. The other thing, too, to be very careful of is now we get into the numbers. These two windows are Zone 3 Energy Star rated. In other words, they are considered to be the most efficient window from Windsor to Whitehorse. The problem is, when you put them in the house, the homeowner is going to feel very different, one window with the other. The window you have, so here's the thing, historically in Canada, and this is almost 45 years ago, the window manufacturers and Canadians said, you know what, we're not the biggest hole in the wall, we let some free heat in once in a while, right? We offset space heating. Okay, so give us some credit. So we came up with this thing called the energy rating, ER. And ER is a combination of the air leakage, the U value, and the solar heat gain coefficient. So you can actually make a window much more efficient, in many cases, by just increasing the solar heat gain coefficient, letting in more heat. Now, at that time it was appropriate. Homes had very little insulation. We used to open windows when we got too hot. We don't do that now, right? We sort of thought different. But the interesting thing is, in the Building Code of Canada at that time, there were two notes that were made in the appendix. The appendix is non-enforceable, but it's the most important, interesting part of the code to read. And in there it said, at the time, ER, although useful, and an alternative method to complying with the building code to U value, it may not be appropriate for two scenarios. Homes and buildings that have over 16% window-to-wall ratio, and multi-unit residential buildings, because it may result in the overheating of the space, causing discomfort to who? Occupants. Well, guess what? We're there. And what we're finding out today is that those windows, the window on the right, is a very efficient window when it comes to solar heat gain, because look at the solar heat gain coefficient, 0.61. That means 61% effectively of all the BTUs on every square foot are coming into the house. So if you have a south-facing window and you've got 90 BTUs on there on that day, you're getting 60% of the BTUs coming in. The window on the left, you're only getting 20%. The window on the left, though, is a triple glaze window. This window is warmer. Two very different windows. Now, to the consumer, this is really sort of not deceiving, but it's complex. And even some of the window manufacturers struggle with this one. So we would say when you're designing homes for efficiency, forget about ER value going forward. Don't even talk about it. Start talking about solar heat gain and U factor. Keep them together. The other thing to keep in mind is when you do your calculations for your heat loss and heat gain, the solar heat gain number will contribute almost up to 50% of your total air conditioning or cooling load on the house. Air conditioning loads are the fastest growing peak load that we have right now. We've got more windows. The geometry of the house is changing. We're finding that it's actually causing our ductwork to get bigger. We do mechanical design for some houses. We review mechanical design, and we're finding that production track builders have gone from designing ductwork for heating loads because the home's heating loads are going down. Now we're designing ductwork for cooling loads because the cooling loads are going up. So now we have to put in ductwork that changes sizes depending on the season. Have you seen that? We haven't either. And we have comfort issues. We can't maintain static in the line at certain times of the year. It's really weird. Anyways, so it's the biggest deal. This is a little study that was done. A new design manual was done by the NRC. It would be actually really useful for you folks to have a look at. It's going to be available within the next month. It's called Mechanical Design for Low Load Housing. And it identifies things like if you have a solar heat gain of 0.3, which is called mid-range, if you get higher than a 0.61, you can increase your tonnage by a half ton to a full ton just on a townhome. Little sample of this was on an existing home. The homeowner had the choice of picking a window retrofit. He got a window that was very energy efficient, had a 0.68 solar heat gain. We've seen windows in Ontario at 0.71. When they put the new windows in, it would have meant he needed 4 tons of air conditioning in the house. Went back to the window manufacturer and said, actually, I'd like a solar heat gain mid-range. Can you get it to me? He says, sure, why would you want that? He said, well, I just need it. He says, well, it costs me any more? No, that's our baseline. Went back to 0.32. They're now at a 2.5 ton unit. So let's do the math. What's the cost for a half ton of air conditioning over 1.5 tons? Base level, 13 SEER, cheap, the stuff they sell on the telephone lines, right? 13 SEER, $400 a half ton. You go to a really high SEER unit, you're $1,000. So let's call it 400. We just took a ton and a half off. That's $1,200. That's enough to pay for your triple glazed windows. So again, it's about balance with the mechanical systems. Here's one of my favorites. Melinda, you've seen this one. Robert Bean and Jim Larson from Cardinal Glass helped us with this. We were actually building their net zero home, and my wife was questioning, why in the world are we paying so much for these triple pane windows? I said, dear, because they're energy efficient. She said, okay, I get that, but she says, what will they do for me? I said, well, I don't know what you mean. She says, what will they do for me? Like how you're gonna feel? Yeah. So, Jim Larson, Robert Bean, we helped us do a little calculation. We used Astro 55. We figured out that if Rachel is a meter away at what was to be our kitchen table with the kids and I, that she would start to sense radiant heat loss to a surface if it got below 14 degrees C. So knowing that, we ran weather data, we ran Azure 55, we looked at everything else, and found out that if we had put in an old window, a reused window, a single pane from an old home, Rachel was going to be uncomfortable for 3,000 hours. If we went with an Energy Star window, double pane, low E, argon, a really good window, zone 2 window, she was still going to be 500 hours, but a whole lot better. If you go with a triple, Rachel doesn't know she's next to a window. I will tell you, and there's a lot of you in here who will know this, so I'm just sort of speaking to the choir. Out of all the things we did in that house, the tri-pane windows are the winner. 4 kids, 40% relative humidity, minus 20 outside, we've got no condensation on the windows. You can't hear anything from the outside, the neighbor's dogs included. It's dead quiet. We can hear a refrigerator for the first time, and you can sit next to the glass and you're not cold. It's pretty cool. Heating and cooling, be careful. Low load homes should not have complex systems. We often get this wrong. Sometimes we think we need really complex systems to solve low load homes, and we make things overcomplicated for the homeowner. So here's the sense of your loads. What are our loads? Well, here's where it's going to go. Here's your 22 to 2030 housing type. So you've got all these different houses. We've just got standard production homes. Let's take a little bungalow and let's go to Toronto. That house is going to need at worst over the next few years 20,000 BTUs. What's the smallest single stage builder grade furnace on the market? What's the size? It's about a 40, 39,000 output. So now we have a load effectively that is half. That if we put in a standard, smallest size, single stage out there, we have oversized the unit. What's the problem with oversizing a furnace or a heating system? Air source heat pump, GEO, you name it. What is the problem with oversizing systems? Less efficient? Yep. And your homeowners are going to feel what? Weird. We built again, we were really proud, buttons popping off. A brownfield development in the city of Cambridge, Ontario. It was the first LEED for Neighborhoods pilot project to be finished in Ontario. It was on an old CanMet Foundry site. Had 72 townhomes, all LEED Gold, Energy Star, 2 mid-rises. The site was LEED Gold Neighborhoods, beautiful site. I had the responsibility when the condo committee sent in their one-year engineering report to go through it and rectify stuff, right? Work with the team, get things done. For the first time in history, I started to see stuff in that report about mold in basements, high humidity levels, can't get comfortable in the back bedroom of the home on the second floor, rooms over the garage are cold, and I'm thinking to myself, wait a minute, these houses are the most highly insulated, airtight, efficient homes we have ever built. What is going on? And we were about to learn a really nasty lesson. Had Gord Cook, who's my business partner now, come out, had Straub come out and take a look at it and found out that, yep, all our equipment was 120% oversized on the heating. Furnace comes on, shuts off, comes on, shuts off, never runs long enough to push the air to the rooms that need it. Traditionally, our answer is put more ductwork in. Not going to solve it. The reason the moisture levels were going up and the basements turned into swamps was because the air conditioning was short cycling. Come on, turn it off. And the air conditioner does not start to remove the moisture until it is run for 8.5 minutes. In other words, if it short cycles, it cools the air but doesn't dry it, so you get a swamp. And your humidity levels, it's the time of year when your basements are the coldest at 1.5 meters below grade, right? You've got your cycles that follow. You've got cold surface temperatures down there. The humidity rates are going through the roof. It's the worst case scenario. Now, here's the crazy thing. How do you go back to the homeowners and tell them, we're going to solve your problems, we're going to put in small mechanical equipment? This is really sort of odd, but it's the reality. So we know the status quo is we have to get closer to designing. We need to do our loads. We need to understand them. We need to measure them and design appropriately. We know that the equipment we put in is most likely going to run at part load for the vast majority of the year, so we need systems that can be variable in their operation with good turn-down ratios is the old term. I'll give you a sample here that if you really oversize a furnace, I'll use as an example, air heating, whatever it is, that you're going to get a system that's going to run for maybe 10 minutes on average per hour. But if you get closer to right sizing it, you can double the runtime, which is important for delivering the system air. Yeah. Two-stage system. It's not just about efficiency, it's about let's get the runtime up. You want to go even further? Go to fully variable. Okay, now, be very careful with this, right? But again, this is why we're starting to see it gets a little more complex. Low loads are weird, because you have to adjust to people's comfort and make sure it balances the home. So cooling loads, yesteryear we used to require, cold air requires more CFM, right? 300 to 400 tons, or 300 to 400 CFM per ton is about what we need on average. Every system's going to differ a little bit. And then you need about half of that for air that's hot, because cold air is cold and heavy, so it's more dense, right? So the cooling loads were smaller, heating loads were higher, but it meant that the ductwork leveled out at about the same size. Well, now that the heating loads have dropped because you're doing all sorts of cool stuff to the envelope, and yet the window sizes are going up and so heat going up, it's doing this. And that's where we get the ductwork that is the right size for the summer, and yet it's too big for the winter. Medium density housing, when you get into multifamily, this is having a big impact as well too. We're starting to see issues where we have various temperatures on different floors, and it's almost to the point now because of glazing and the envelopes and the low loads that you have to do zoning just to make people happy. It's not really something that's a luxury anymore, it's something that almost has to be done. The other thing too that I want you to keep in mind is that low load homes, if you're principally using forced air systems, air source heat pumps, geo systems like that, you have to remember that you're actually moving, in some cases, air at a lower velocity. You might be using higher volumes over consumer time, but you're actually losing low velocity. And what we're finding is we're starting to get homes that have lots of stagnant zones in them. So areas where the air is not mixing. So traditional duct systems are designed on what's called displacement. In other words, the air pushes into the room through a register and it displaces the air out where? Return air. And that's what it was designed as. What we have to move towards is this thing called heating and cooling and conditioning by diffusion. In other words, we need to start to mix the air. In the residential world, we don't even know what it means to look at a register and talk about throw. In the commercial world, this is very important because you need to mix the temperatures in the room without affecting the homeowner. So we are starting to see the use of diffusers on high wall. We have enough insulation in the exterior walls and the windows. We don't need them below at the floor anymore. Besides, people put their beds on top of them. Did you know that? Yeah. So let's get them off. Let's get rid of some ductwork. Let's put high wall. Let's move the air a little faster, not high velocity, mid velocity. Let's get it out of the occupied zone, 6 inches from the ceiling, and let's start to mix the air quietly but effectively, and start to mix the air in the room. So again, right now there are some issues with the ability to do this. You either need a PEng to sign off for you or they won't accept it, but the HRAI design guidelines for air system design is currently being redone, and it's going to change this so that designers for residential can actually do up to 1 static or higher, which will make this happen. And the requirement to put registers under windows and doors will be taken off. So keep in mind that is coming. So you start to get systems that work like this. They push air a little bit faster, they do a little quieter, but they're actually mixing it. They use the ceiling sort of as a plenum a little bit with the Quandra effect, and that's the way it works. Heat pumps, we're not going to spend too much time. We are seeing a lot more heat pump use out there, whether it's geo exchange or whether it's air source. And again, it has the big thing we're faced with in Ontario in particular is the fact that we have natural gas, and it's awful because it's cost, right? It's hard to have the carbon conversation with some consumers when it comes down to the cost of operation. Now, that said, on my own home, we were not in Enbridge territory, so we had to use electric, right, or propane. Our load was so small in our home that when I looked at geothermal versus a really good air source heat pump, cold climate, I could not justify doing the geothermal. And now we're doing it with a cold climate air source heat pump that I ran to -28 and it still didn't go to backup, which was sort of cool. So the good news is low load homes, lots of different options out there. Guys, it's on VRF, VRV, you talk to them, they'll figure it out for you. This is the air source heat pump at our house. Our net zero home, way oversized, it's overkill, but we're doing a study with Mitsubishi. This is actually a commercial-based system. Couple things on the residential side. Manufacturers will only give you the HSPF performance levels for zone 3 and 4. They will not give you your correct zone. So they're going to tell you have heating seasonal performance factors that are incredibly high. You've got to derate them. And good luck finding the data. I know MITS and Fujitsu, you might be able to find it, but you need to look for the right data, first of all. The other thing too is, on the cooling, it's great. It actually will ramp down to just humidify. We had our first year in the home, it only went on full cooling 3 times out of the entire summer. The rest of the year just dehumidified. So that's really nice. The other thing too is make sure you put them on rockers. Learned a bad lesson. Every Saturday I was out with a pneumatic hammer for the first 2 years, taking the ice out from underneath. You can do that. You can put it on a slab in Alberta, and you don't have a problem. It's minus 40 out there. They have no moisture in there. It doesn't condense enough. You put it here. I had 20 inches of ice underneath this. Again, humidity levels. Hydronic heating, absolutely. Again, I'm just sort of going to flip through some things. We are seeing a move towards hydronic, even with the production. We're finding that there is an affordability measure here, that yes, they do cost more than forced air, but we're starting to hit the sweet spot because the loads are getting smaller. You need less pipe, you need less pumps. You can actually design simplified systems. And keep in mind, from a science perspective, 16,000 BTUs with a half-inch pipe with water, 16,000 BTUs with a piece of ductwork. It's actually nice when you get homes with geometry that's odd. You can move the heat around a lot easier with a hydronic system. Naturally, it is a radiant and floor heat, is a zone system. It's very comfortable. It addresses this mean radiant temperature issue very well. It's ideal. We often say if you're not going to put radiant in and you're going to do a basement or a slab, just rough it in, throw it in and keep it there. We have some of these net zero homes that we've done that just did auxiliary heating in the basement for floor warming, and the main system of the house never runs now. It just runs off the auxiliary in the basement for most of the year. The other thing is testing. Again, if you haven't done testing, I'm not just talking blower door, I'm actually going to show you these other things on the mechanical side. Testing static pressure in your system. It takes all of 5 minutes for somebody to check the static pressure in a forced air system. If you don't have enough static pressure, you don't have enough gas in the tank to push the air through the rest of the house. It's the single biggest issue we're finding in the field. Ventilation. Keep in mind, of all the good things we can do, we can use good products that have low off-gassing. We can do products that have low carbon footprint, but I want you to keep in mind that every home, or actually the only homes that need ventilation to maintain air quality are those, like I said, that have breathers. Right? And here's the thing. The principal thing that affects breathers from an indoor air quality is really still, the number 1 item, lack of proper ventilation. So it is a cornerstone. Do all the other things, but make sure you do this thing right. And again, Canadians have known this for years. A couple other things we sort of forget once in a while. Natural ventilation is good. Use it appropriately, but be careful with the general consumer. Natural ventilation will work when you have proper pressure differentials. It'll work when you can do some interesting designs, but you often need a mechanical component to make sure it works year-round, full-time, because people, believe it or not, breathe most of the time they're in the house. Minimize by design. You've got to have a pressure difference. You've got to be careful of moisture loads as well when you're using passive ventilation. You can actually get into issues with humidity control if you use implies cold draft. Some people don't like to feel the air, and it's not evenly distributed. Remember, one of the tenets of ASHRAE 55, one of the tenets of 62.2, the tenets of good IAQ is not just to get the fresh air into the home, but where does it need to go? To the rooms where the breathers are. And which room do we do most of our breathing in? Respirations. Bedrooms. Right. So that's called ventilation effectiveness. Not efficiency, effectiveness. It's getting the fresh air to the rooms you need it. How are we doing on time, by the way, Tim?
I think we're good. You're here till lunch, right?
You guys okay? Take a part.
let's
Okay.
keep-
Okay.
take a break.
Hierarchy of IEQ. Are you guys okay if I keep going? We'll finish up right at 12. You want to take a break? Keep going? Okay. It's okay if you go get coffee. Just bring me back one. You just need a black, no cream. The hierarchy of IEQ. Number one, remember, keep the order of priority right. Sometimes we lose the order of priority. I'm going to make fun of the guy in brown overalls. You know what I'm talking about, right? Clean t-shirt. Builds perfect homes in 36 and a half minutes. Okay? I actually think he's a pretty good guy. I think he tries to do what's right. I just like him to not say some things sometimes. But here's the thing. I'm going to make fun of Mike for just a minute. He had this thing called Bluewood. Remember Bluewood? Going to build a house, decay resistant. Water Management 101. The master builders in Europe knew this after going to school for 50 years on how to become a master builder. First principle of water management is what? Is it building with decay resistant materials, or is it deflection? What's the second one? Not decay resistant. What's the second? If you can't deflect the water off the structure, you have to drain it. And if you can't drain it, you have to make sure the assembly will dry. And the very last thing you do, worst case scenario, is you build out of decay resistant materials. And that's what I mean. Make sure you get the order of priority right with some of the building science rules. Building with Bluewood means you've got problems so bad with deflection, drainage, and drying that the house has to be built that when it gets wet, it won't rot. That's another conversation. Ventilation systems, a couple things again we often forget. Ventilation does not provide makeup air. Okay? Got it? Your range hoods are on their own. How many of your clients like helicopter engines in their houses?
I cook.
You cook?
Coffee.
Rose coffee?
I'm going to use a big range hood.
Thanks, Melinda. Here's the interesting thing. I'm out at the Builder Show, the big NHB Builder Show. If you ever want to go have a grand time and get a few good laughs, go to the big Builder Show out in Vegas or Florida. It's really interesting. It's sort of cool, but there's a lot of stuff you just shake your head at. 7 booths with range hood manufacturers. 200 CFM to 2400 CFM. How many of you design commercial range hoods for restaurants with grease traps? What's your typical CFM of a typical hood? Worst case scenario, right? You've got grease, you got fries, you're cooking your deep fried 400, 500 CFMs, usually it is, but usually like ASHRAE will drop you 400 to 500 CFM. It's not about the CFM, it's about the geometry of the hood. It's about capture efficiency. CFM doesn't really do you a darn thing. You design according to ASHRAE, it's geometry of the hood, does it cover the geometry of the burner? And it's 4 inches to the side, at the back with the flat surface, at the front overhang by 4 to 5 inches. If you go to 6 inches, a recent article by ASHRAE said you get a 5% boost in capture efficiency. Range hoods, 500 CFM over the range microwave. Overhead the microwave stops at the face of the cabinets. It misses the front of the burners. It gets part of the back burners and that's it. Even at 500 to 600 CFM. It's geometry that's the difference, it's not the CFM. The other part of it is that it doesn't get enough air, but we'll get there in a minute. Ventilation doesn't provide combustion air. If you are using gas appliances, your HRV or ERV is not going to provide you fresh air to overcome that. That's a different story. Balanced ventilation, whether you, with an ERV or an HRV, whether the window or doors are open and closed, it doesn't matter, it still works because it has 2 fans, right? Air in equals air out, building science principles. It still works with windows open and closed, which is great. Forced air heating and cooling to load, just one we have to remind builders sometimes that you can turn the furnace fan on all day. It's not going to bring in fresh air. It's just going to bring the stuff from the basement upstairs and upstairs, downstairs. So, again, basic principles. The type of ventilation we want to do in this climate is which one of these systems? Exhaust supply or balanced? Balanced, exactly. And that's where we are with the Ontario Building Code, believe it or not. Hooray, hooray. It only took us, 40 years. My business partner, Gord Cook, selling HRVs for years to people that know what they are. Gord can die and go to heaven happy because HRVs is now the number 10 item on the list we just saw. Right? Oh, thanks. I'm going to talk even faster now. So, balanced ventilation. I find it interesting in the U.S., there's actually even some passive projects and zero energy, what are you doing, that they'll do the balance and they'll do a fan in and a fan out, but they just can't quite get their heads around the heat exchange yet. Just trying to, but I love it. We're all there. We got heat exchange. So now let's talk about the next step. With low energy homes, you need mechanical ventilation, not just passive. You can make them work together. You need balanced 2 fans. You need heat, not just heat. You need to look at enthalpy, right? The energy and the moisture as well. And what we're looking at now is it's not just the system itself. You need to get the fresh air to the rooms that need it. You need to distribute it appropriately. I had a homeowner out in Nova Scotia, lived in a net zero home after 1 year, and he was really concerned. He wanted to do IQ monitoring and he wanted to measure CO2 levels in the house. We had monitors all over the place. Found out later why. He's a submarine captain. Balancing and tagging units. This isn't the end of the world. An HRV and an ERV is not going to put a house under too much pressure or too little pressure to cause you envelope issues. However, it will cause an issue with the efficiency of the unit. Make sure your mechanical guys balance them. If there's not a sticker on the box and they've balanced the intake and the exhaust to within 10%, tell them to spend the extra 3 minutes and do it. And if they won't, buy them Timmy's, bring them out to site, watch a little YouTube video for 5 minutes and teach them how to do it. It's actually building code. The stickers come in the boxes. HRV or ERV? How many of you are using ERVs? Sort of cool, isn't it? 8 years ago, I Googled ERVs and it told me I couldn't install them north of the Mason-Dixon line. Right? ERVs typically will only be used in warm climates. Some manufacturer will go, oh, you can't do that. Like, the core's going to freeze up and the door's going to shut on you all winter. You're not going to get fresh air. Well, just wait a minute. A couple things we're learning is that the moisture loads in homes are going up, and more homes do have some sort of air conditioning. And the ability to actually keep the moisture that is created in the house in the home is helping us keep moisture levels where they should be for hardwood and for the occupants. We had 2 children at the time. We had an HRV. I was proud of it, big brown box in the basement. Rachel calls me one day and says, Dr. Naidu, the pediatrician says we need to turn the fresh thing off in the basement. I said, we can't do that. She says, honey, it's 15% relative humidity in the house, and it's why the kids are getting sick. I said, well, we can't, because Gord Gook says if we're breathers, we need a fresh air. She says, I don't care, I unplugged it. So I called Gord. Gord, what are we going to do? He says, don't worry. He says, an HRV can be off for a day, day and a half. You're probably going to be okay. He says, we're going to turn it into an ERV. And it just so happened to be it was a Vanny unit that you could swap the core out. And I said, Gord, you can't do that. I'm telling this to the original Vanny guy, right? Gord, you can't put it. He's like, Andy, trust me. So he comes out, he puts an ERV core in. I'm really scared because you're not supposed to do this in a cold climate. Our humidity levels in the home in February went to 40% and stayed there. Kids are healthy. Rachel's happy. I'm happy. Breathers have fresh air. Sort of cool. Didn't need to put a humidifier in the home. Now, that was for us. If it's 2 people living in a house 50% of the time, in and out, lots of hardwood, they might need a humidifier. They might not create enough moisture to put back into the house to keep the levels there. So it's all about occupancy. The other thing too is cooling. Here's the problem. If you do have cooling systems, it doesn't matter if it's a mini-split, multi-split, whether it's a central air system, an HRV simply brings in fresh air, which you need. The problem is it's also full of moisture in the summertime. And what do they tell you to do in the summertime? Turn it down, summer setting, or off. Well, guess what? Are you still breathing in the summer? Yeah. And if you had air conditioning, are you opening your windows during the day? No. An ERV allows you to continue to use your air conditioning because what it does is when the air is already being pre-cooled by the air conditioner, it vents the cold air out and it actually pre-dehumidifies the incoming air. It adds, I think some of the studies at the CHT homes said it adds about 20% efficiency to the air conditioner over and above an HRV. So again, something that we're seeing. The other thing next step is we sort of have taken a step back. We've been really concerned that we need like 90% efficient HRVs. We're going to go buy a $10,000 Zinder and we're going to put it in the house because by golly, it's really efficient. Well, here's what we're finding now. It's not so much the heat recovery that we're concerned about with energy efficiency. It's actually the fan motor that's the concern. So efficiency, yes. Here's just a quick example. In general, a 65% SRE to about a 90% recovery will reduce about 0.8 gigajoules on a low load net zero home. So that's pretty good, not bad. But by going to ECM motors, it's a 2 GJ reduction. So again, we're going to say get your efficiency up, 65, 75, that's good. Get to an ERV. Next, before you go any higher on efficiency, get to an ECM motor, and then the last step is to go out and find that world-class 90%. But it's the motors that become sort of the low-hanging fruit. And again, keep in mind 3 types of air you need in the house: ventilation air for breathers, combustion air if there is fuel burning appliances, and makeup air just for your range hoods. We've already spent time on that. People say, well, how do I know if I need a makeup air for a range hood? Well, I'm going to tell you, if any of you are doing tight and light houses or net zero homes, you're likely going to need what we call a makeup air, or some sort of a hole in the wall that opens up if you've got a range hood that is over 350 to 400 CFM. Because you got to remember, with blower door tightness at 1 or less, that you guys are doing 1.5, when we put the door at like high speed, the big funny door, at a 50 Pascal pressure difference, we're only depressurizing the house at like 500, 600 CFM. You're going to put a range hood in at 400? By the way, do you know how to do a redneck blower door test? We get called out to do blower door tests with thermal imaging cameras to find the leaks, right? So we just say, buy your own camera, we'll show you how to use it, but then turn the dryer on, turn the range hood on, turn the bath fan on, and you now have what we call a redneck blower door test. So, hole in the wall. You don't need a preheated hole in the wall for residential. Unless you do really large ranges, you might need for 1,000 plus CFM. But for the most part, up to 800 CFM, which is about all you need for actually up to almost, I think it's almost a 5 to 6 burner gas. If the geometry is right, you would need 600, 800 CFM. Braun, Newtone, these manufacturers, without telling you, have started to put low volt taps in the back of the range hoods, and what they're there for is to connect a low volt wire down to the basement or the utility room where they have a hole in the wall. It's a mechanically operated damper that it's really complicated. When the fan turns on, the hole opens up, and when it turns off, it closes. Or like one of the builders we had, I think it was Marshall Holmes and Bob Cajun, one of the guys anyways, got so frustrated with the whole range hood thing that he had his electrician wire tap on the kitchen window with the low volt to the fan, that the homeowner couldn't run the fan until he opened the kitchen window. That's the other way to do it. So, net zero, again, let's talk about humidity control, because we're on ventilation. This is, again, why this is so important. Relative humidity is what we're finding out to be the real big issue with health in these low load homes. Robert Bean would say, along with ASHRAE, 35% to about 40% of the winter. In the summertime, maybe as high as 55%, but somewhere in that range, because if you get too high or get too low, you are at risk of a lot of different things. You've got studies like this. Again, Robert shared this with us, Melinda and some of the others, Chris would know of these studies. They actually show in hospital environments that if you're not careful, you get too much or too little, you actually start to be not only more susceptible to the flu, the colds, but you also, the rate of transfer goes up. So again, controlling the relative humidity is ideal. And again, ASHRAE, if you want to know what the book says, cold climates, what the Building Code of Canada assumes, it's 35% in the wintertime is what it's assuming. So not too much, not too little, and we don't like this stuff either, just so you know. This is where the homeowners get concerned. Now, we're going to go off the deep end. A good friend, John Straub. This is an interesting one. It's one we're hearing talked about. It's been around for years, but it needs to be talked about a bit more, and it's about the fourth state of water. So water is a liquid, a solid, and a gas, and there is one other state, if you will call it, it's adsorbed moisture. And this is really important, and the reason it's important is because you happen to build with materials that are porous. And the reality is we're no longer just concerned with water that's at 100% relative humidity at its dew point. We are now concerned with air that is 60 to 70% relative humidity. And this is really important for us to understand. So here's what happens when you get into adsorbed states of moisture. Thanks to John and the team at RDH, borrowed some slides that they gave us to use down at our CI lab in the US. When you have relative humidity of about 20% in a room, invisibly on objects and surfaces, you will have an invisible layer of water molecules, right? Water likes to cling to things. Surface tension, right? Think meniscus as kids in grade school, right? Surface tension, capillary action. And that single layer of water molecules are clinging strongly to those surfaces. You don't see them, it's no big deal. As the humidity goes up, the layers add up. And when you get up to 5 or 6 layers or so, the top layers are now not hanging on very tightly, and they're bouncing back and forth with the air. That's the stage at which we actually start to see condensation start to happening. But here's the issue. Even at lower relative humidity rates, let's look at, let's say, 50 to even 60, you've got 2 to 3 layers of water molecules that are invisible, that you can't see. And it's fine on materials that are not porous. But when you get to materials that are porous, here's what happens. The pores, those 2 to 3 layers of water molecules in a pore now add up. And what happens is you start to get a curve that looks a little like this. Some of you have actually seen this. When you get interconnected layers, so wood, paper, cardboard, you don't need 100% relative humidity. You don't need 90% relative humidity. You don't even need 80 for you to start to see mold growth, sporulation, or spread. You only need 60 to 70% in porous materials, because in the pores, you have a concentration of water now. So that's why this 4 state is incredibly important to understand. I'm not going to take any questions on this. You're going to ask John or Chris or some of these other folks that are smarter. But this answers a lot of questions for those of us in the industry that are just practitioners. Why in my basement or in my house do I smell weird things when the humidity is only 60%? Porous materials. So again, the control of humidity starts to be very, very important. To dehumidify or dehumidify, it's lifestyle driven. And folks, here's the overall thing that we have decided. Low load homes, we are coming to a day where we will not only have to have a system that heats and a system that cools, we'll have to have a system that ventilates, and we will now have to have a system that is specifically there to either humidify or dehumidify, or both. We've relied on HRVs to do what to the air in the house? What's the byproduct of ventilation with an HRV? Dries the air. Guess what? That's not what it's there for. It's there to do what? Provide air for people that are breathers. The byproduct was it dried the air. The problem is we can't rely anymore. We still need fresh air. So in some cases you may need a humidifier with a house that has an HRV. You may even need it with a house that has an ERV. It's all about lifestyle. So how do you look at this? Occupant loads, people, pets, plants, lifestyle. We often say wait a year to figure out whether you're going to need a humidifier or dehumidifier. Do you have hardwood in the house? We've seen engineered hardwood blow apart at 55% relative humidity in a house. 55. Engineered hardwood manufacturer warranty states between 45 and 55 is where they like it. Anywhere below that, they will not warrant it. And we're seeing engineered hardwood floors have issues with levels that are too low. So again, you've got to understand the occupants. Pets, for goodness sakes, the average North American domestic household pet has 3.5 times the respirations that you do. Did you design your ventilation system for your cats? I'm joking, but it's true. Did you know that short people take cold showers? Where's the engineers in here? Falling water loses how many degrees per foot of fall? Come on, you complain in a hot tub, it's not 104, it's only 102. Well, guess what? The shower head's 2 feet up. My wife's shorter than I, she gets in, it's a 2-degree difference, and it's a big deal, right? Short people take colder showers. Okay. Importance of humidity control, some other things to consider to control this that you can look at. Air conditioning. Don't do anything less than 2-stage units at minimum, so it can actually slow down a little bit and get a proper cycle time. And in some cases, if you go with mini splits, multi-splits, they have actually dehumidification cycles that can do that alone, and they're great for ERVs. Nice option, whole house humidifiers, dehumidifiers, ERVs. Windows, Velux has a phenomenal system. We've done some modeling for them on a research project where it actually will look at the indoor and outdoor ambient temperatures, relative humidity. It'll actually look at the weather forecast and start to decide whether with the window openings alone it can affect not just ventilation but relative humidity, and it's interconnected with the mechanical systems of the home. So again, sort of cool. Complex, but it's interesting. Keep it simple. Hot water, I want you to look at the slide again. Here's the thing. Space heating is almost identical now to hot water heating. And this is important to understand. Our hot water loads are not going down. So it now becomes really equally as important as heating and cooling in the house. So hot water loads, we've come a long way in a long time. It's something that's becoming a bigger deal. Solar thermal has been around for years. We still are waiting to have a really good turnkey system out there, but there's a huge opportunity with that. Most of the time in low load homes that we're seeing is air source type heat pump systems. The good news with these systems is you have typical split systems, and you also have package systems. The package systems are the one that the condensers on the top. I can tell you I have one running in our own home right now as a study project. It is incredibly quiet. The recovery rate is about 1/3 of our Navien, next to it, that we're testing as well. But we've doubled the recovery rate by doing preheating through drain water heat recovery. It works really cool together, by the way. This is a perfect match made in heaven. And here's the building science lesson 101. 1 + 1 doesn't always equal 2. 1 + 1 can often equal 0.5 or 3. So I'll give you an example. Drain water unit we have installed in our home is a 72-inch unit. Gets all our showers. It preheats the water, but it preheats the water when we run the Navien hot water tank so warm that our unit only condenses 1/4 of the time on showers, which means the overall efficiency is actually less than what we get typically out of the condensing tank. However, when the air source hot water tank runs, it's really cool. Cool, seriously. Now, with the units like this, the new systems, the Rheems, the Sandins, which are really efficient CO2-based systems, they now have duct kits, and this is fairly new. They didn't used to want you to put a duct with the rejected cool air coming off. They wanted it to stay in the room, and they were concerned about freezing the coils internally. Now the new systems come with a duct kit, so when it uses the air out of the room to heat the air, it rejects the cold air. You can either do it back outside, what we have in a couple of projects we've done, we put it back into the forced air system, which is really cool. We found it has negligible effect on the heating and comfort levels of the house at all, but in the summer, when we take showers in the morning, we get free cooling. So that technology is old technology, by the way. So water conservation, again, don't just look at the equipment, look at, plumbing layouts, look at manifolds, hot water demand system. Here's the thing that it's doing. It's understanding that if you design a plumbing system correctly and you right size the pipe, you can minimize the amount of water that is sitting in your pipes. The problem is the building codes have forced us to increase the size of pipe, and they forced us to put on low flow fixtures, which means we have more water sitting in the pipes. In fact, so much that in some of the cities in Ontario, it actually causes the water the quality to drop because all the treatment is settling to the base of the line. So in Rockton, Ontario, there's several businesses that have to run the water for 15 minutes every morning to stir the stuff back up in the water. This is where the building codes don't work together sometimes. Anyways, good news is right size the pipe, shorten the runs, and it decreases the time from tank or source to tap, just like you would do with a pump. Solar, I don't want to spend too much time on this one. Only like to say that it's about making correct decisions. I'm not saying this isn't a right decision. I think this is sort of a cool house, and I'd actually like to tour it someday. But let's keep in mind, what we have found from the studies with NRC and from our builders and myself as a builder is it's about 60 cents to $1.20 to decrease the use of a watt, better insulation, better windows, better air types, better mechanicals, versus how much is it for solar to create a watt?
$1.90 to $2.20,
depending, sometimes scale size, yeah. Depends where you are. I would say maybe 2.5 still, but yeah, okay. But it's about finding the balance. Not saying you don't do it, but do one thing first and then do the next thing next. So it's about doing first things first is what we're saying. Building technologies, and again, you folks will know more about this than I do. We've done a lot of work with Sonnen. We're doing some of the first studies on some of Tesla's stuff, which is sort of interesting right now with some of our stateside clients. Pulte and Lennar are both looking at their product. All what we have seen is we are moving very swiftly from panels to building integrated PV. We're going to see less and less efficiency gains on panels. We're going to actually see less manufacturers of that product over the next 5 to 10 years, and we're going to see it swiftly moving towards building integrated PV. Dow alone spent $1.3 billion on the Powerhouse product. They've now sold it to another firm. We did the first install of the product actually on Gord Cook's cottage up near Southampton. It works very well. The only issue for those of you that have done building integrated, you'll know that the efficiency per square foot is about half of a panel. Now, the Dow Powerhouse, the efficiency has come up. There's now IST, Integra solar shingles that are about 75% as efficient as a panel per square foot, so that's where the R&D is going. So just something to keep in mind. Battery storage, and again, folks know more than I do, we've got a couple of projects now where it was actually more cost effective instead of putting a Generac backup on a cottage out in the woods, put a Powerwall, a couple solar shingles. It was basically cost neutral. This is sort of cool, because now we question the grid, right? And it's not just people in cottages, it's people in houses going, you mean to tell me that the bulk of the bill I'm going to be paying this month has to do with the fact that there's a line in the ground? This company, by the way, Sonnen, who were they just bought by 3 weeks ago? Not quite. Not quite. Shell. And here's why. What's going to happen to the gas stations? Yeah. Where are they going to go? It's going to be power stations. And how do you store energy? Okay. Anyways, it's sort of cool. It's a cool time to be alive. Almost at the end. Bear with me here. Just some things that we see on the future. This is a builder we've worked with for a number of years. It is a production builder. I think he's one of the best examples of what production builders are capable of. They continue to change. It's a 30-year-old company. They're going through some hard times right now because their principal operations in Alberta and things aren't so great out there right now. However, they were the largest builder by volume in Alberta for many years up until the downturn. They now build in Arizona and they're moving into Denver. They actually are the only LEED certified modular building plant in Canada. So this is landmark. They have, the company goal was by a year and a half ago that all product would be at least net zero ready. 2 years ago they launched what they called Canada's first full affordable net zero home with solar. For something like $398,000 you could buy a 1,700 square foot single detached home with a garage with solar in Edmonton, minus 31 degree day, for $1,000 more than the average price of homes in the Edmonton area. But remember, it took them 30 years to figure it out. So it's people like that you want to learn lessons from. They're vertically integrated. Everything is built in the factory. It's not your typical modularization. They actually had to develop their own CSA standard to actually approve their stuff. So it's wall sections with insulation with some integration of mechanicals. The home is sent to site. It's actually installed, put together within 11 to 15 days. Sort of a cool company. Reza, if you ever wanted a really good speaker, very gracious man, great guy, shares everything else. You folks drive the cars that the company that builds these houses, right? It's called Toyota. Toyota builds, I think, at their top 3,000 or 4,000 homes a year in Japan. Their backup storage source for their home is their full plug-in Prius. Toyota owns a company called Sekisui Homes in the US, which is now effective as of, I think, 2 months ago, one of the largest builders in the US. They're buying up modular builders left, right, and center. They're competing with Berkshire Hathaway, who's doing the same thing. All the home construction is modularized. You can call them up, you can order the modules, you can order the whole house, or you can order just the bathroom that will come compacted and dropped into your structure. But their baseline homes are net zero in Japan, and the reason isn't because they're so concerned about climate change, it's the fact that, guess what's expensive in Japan? Electricity, yeah. Cool project. If you ever want to take a look at it, the one that's coming up, it's lots of opinions about it. There's the Markham, there's 17,000 lots to be developed in the city of Markham in the next 12 years. The city has said to the developers, we want you to do nothing less than net zero ready. It's caused a lot of stir, can you imagine? Mattamy has chosen a 300-unit subdivision to trial full geothermal. So the entire site will be geothermal based, and they're looking at building the homes, the loads being proportional to low load net zero homes. This is the site in London, W5. This is a really cool project. How many of you have followed this site, had a chance to tour it, or know about it? They have a learning center now, I think, that's opened up. You can go to. It's sort of a cool site. They took 7 years figuring this site out before it went in the ground. First 110 units are in. They've got their office building, which is net zero, which is done. They've got several other communities going in. Here's the thing that they had to deal with as a large production builder. They designed the community. We did load assessments on the residential. Another engineering firm did it on the commercial. Everything was going fine until we met with the utilities. And we're sitting at the table with the Enbridge and the Union Gas and the London Hydros of the world, and it's really quiet. And the reason it's quiet is because these buildings and homes are using so little energy that the folks that are supposed to fund the infrastructure can no longer afford to do it. Especially the gas people, because guess what? Their funding mechanism is based on what's called the Dream Calc, which is guided by the OEB. In other words, they couldn't even possibly do the math. In other words, they had to tell Sifton it's $5,000 to $6,000 a door, every unit, just to put gas on the site. So you know what Sifton did? It's all electric. They've got some main gas for some cooking and maybe some industrial uses going in, but it's all electric. So really efficient air source heat pumps, net zero levels. The interesting thing is most of the units they put out there are lease units, and they were purchased very quickly. Anyways, you ever want to tour, Rick Guer's executive VP down there gives a great tour. It's a great website to look at. So real quick in review, codes are changing, consumers are changing faster. If you keep up with the consumers, you're not going to have to worry about the codes and the standards. If you build a house for their comfort, you don't have to worry about the energy efficiency. Get my drift, right? Better windows, better walls. Benchmark. You can't improve if you don't measure, and once you do measure, you magically improve. It ain't just the blower door test, it's not just the IR. What else are you going to start measuring? Mechanical performance, cycle time, humidity levels, do some really cool stuff, IAQ. The only truly sustainable home, this is a motherhood and apple pie, are homes that are built with good science. If you don't use the science, it's not sustainable anymore. Learn from others, make some mistakes, talk about your mistakes because it's cool to hear about them. And the last one is being a learning company and team. There is a concept, you guys will be way ahead of me on this one, companies that are effective today, B corporations and others, are companies that are identifying themselves as learning corporations. And they're companies that know that if we're going to be successful and we're going to be safe and we're going to be smart, we have to be able to learn and make some mistakes. How many of you were forced to read Alvin Toffler's book, Future Shock? I'm not going to say this right, but I remember one thought out of that. He says something to the effect that the illiterate of the future are not people who cannot read or cannot write. They are the people who cannot change and adopt and change again. So there you have it. Thanks, folks.